Whether you are a software developer, a data scientist, or a tech enthusiast, this course is designed with your aspirations in mind. Join me and let's build something interesting together. Building applications that first establish a ground-level understanding of what are large language models. But before we go large, let's visit the idea of language models and tokenization. Language model is a probability distribution over a sequence of words. In plain English, it means the language model takes a context and predicts the next word in the sequence. So as an example, when we ask ChatGPT a question or context of shaping tomorrow, the language model behind it will predict the next word with, and it will concatenate the predicted word and send in shaping tomorrow with to the language model again. And we will get back the word AI, so we concatenate them together again and send them to the large language model and get back the word applications. And we repeat the same step and get back the word called end of text. This concludes the sentence generation process, and we end up with a sentence shaping tomorrow with AI applications. You might wonder what end of text is. It is a special token that denotes the conclusion of text generation. So this brings us to tokenization, or how we chunk up text for language models to understand. Tokenization means we split text into chunks of tokens and map each token into a number so we can process them using computers. OpenAI chose to use a very efficient algorithm called byte-pair encoding to tokenize text. It was first invented in the 90s as text compression algorithm that used a count-based method as heuristics. Due to byte-pair encoding, the tokenization results might not make linguistic sense. So to see tokenizers in action, let's go to platform.openai.com/tokenizer. As an example of tokenization, let's check the word translation. The word translation is tokenized as one single token, translation. The reason is likely that the word translation has appeared frequent enough in the training text to warrant its own token. This is very different than splitting up the word translation into trans, let, and shen, so sometimes this may be counterintuitive. Another example is the word Samantha. It is tokenized into 3 separate tokens, S, Amen, and Tha. This is again the byproduct of the tokenization algorithm. Either the word Samantha did not happen frequent enough in the training text, or the subword Amen happens with enough frequency to break up Samantha into 3 separate tokens. And going back to our special end of text token, there are a bunch of very special tokens that OpenAI uses to process text. For example, 3 pound signs or 4 pound signs are both equally as useful to delimitate text in the prompts. This is important to know because OpenAI charges fee by token consumption. The rule of thumb is it takes roughly 30% more tokens than words. So if we have 100 words in the prompt, we should expect 130 tokens. To get to the most accurate count, we can use the TIT token package. Let's put a definition on large language models. So how large is large? The current standard of large is more than 1 billion parameters, and the model has read more than 1 billion tokens of text. Compared to linear regressions, which usually have only a few parameters, this is a significant increase in size. So what happened was that when we scale out compute and data to train language models on enormous amount of data to predict the next tokens, reading the whole internet to predict the next token, and only predicting the next token, we surprisingly found that large language models start to exhibit emergent abilities. This was discovered in 2022, and we found that we can now prompt it to do arithmetics. We can ask it to do machine translation. We can even ask it to provide some reasoning capabilities. All these are very amazing to observe. And in summary, large language models can now be prompted to do many tasks. Next up, we will get our hands dirty and start building the first part of our Chat with PDF application. Understanding of what a large language model is and how it works under the hood. It's time to get our hands dirty and start building our Chat with PDF application. Our first step is to provide a front-end interface for us to interact with our large language models. Here, we are introducing a large language model application front-end framework called Chainlit. Chainlit is a native Python front-end interface that is designed specifically for large language model applications. This is their website, and this website has a very comprehensive documentation on how to get started. So as a first exercise, please go to our GitHub repository, click on Code Spaces, and once clicked, it should show up with an interface similar to this. Then go to the app folder and navigate towards the app.py file. The first step here is we will create the Chainlit application that when a user types in a message, the application will echo the message back. Here, we have prepared 2 exercises. First, please add the proper decorator to the main function so Chainlit will call this function when it receives a message. And the second exercise is let's try to get the content of the Chainlit message and send it back as a response. And this should complete the echo application. To run the application, we can go to the terminal and type chainlit run app/app.py-w in the terminal. Once done, our application can be run by typing in chainlit run app/app.py-w in the terminal. Have fun. So the first question is we need to add a proper decorator. So this main function will get called whenever Chainlit receives a message. So we use the onMessage decorator, and then we will try to echo back the content of the message back to the user, and this completes the scaffold. So to see the application, we can now type chainlit run app/app.py-w from the terminal, and this should pull up an application from GitHub Codespaces. Cool. Now in this application, you can type in anything and Chainlit will echo back whatever we send it. So as an example, when I type, I love LLM apps, it will echo back the same sentences. Next up, we will try to understand some basics about instructing and prompting large language models. About large language models, we know now they have emergent abilities that we can instruct them to do many, many different tasks. The way we instruct them to perform tasks is by using prompts. A prompt is a user-defined input to which the LLM is meant to respond. In case of OpenAI models, we will be using a specific markup language called Chat Markup Language, or ChatML. In ChatML, we separate the prompt into arrays of roles and contents. There are 3 types of roles: system, assistant, and user. System is the system prompt where we provide instruction to the whole system. This is usually set at the beginning of a session and not changed. The assistant role is the language model's response, and the user role is for user inputs. So in a conversation, we can expect the list of prompts goes from system to user, and then the language model responds as assistant, and then user replies back as user, taking turns in making the discussions. To facilitate communication between users and language models, it is very common to use a prompt template. Prompt template is a predefined recipe for generating prompt. Langchain provides an abstraction for building prompt templates. As an example, here is a prompt template for chat. In this prompt template, there is a system prompt and a user prompt. In the user prompt, we provided a variable called text using Python fstring. So when we use this prompt template, we can substitute the variable text with a literal string. The string will be substituted in to the template with the user-specified inputs. Once substituted, we can then send the whole thing to the large language model for it to generate answers. So now, we can grab an OpenAI API key so we can add large language model to our Chat with PDF application. OpenAI's large language models, we need to obtain an API key. So to acquire an API key, let's navigate to platform.openai.com, sign up for an OpenAI account, log in, and hover over the icon to the left. There is a lock icon that says API keys. And when you press on this, it will show up, and we can click on create a new secret key, provide it a name, and click on create secret key. And this key will show up. Copy, paste, and store this in a very secure place. A leaked API key is a security hazard, and it might cause you to lose substantial amount of money. So make sure this is stored safely. I will delete this, and that's it. Now we have an API key. We can add large language models to our chat app so we can have our own basic version of ChatGPT. Let's try to add large language model to our Chat with PDF application. First, let's make a copy of .inf.sample, rename it to .inf like here, and put your API key inside this quote. Now, to build a large language model application, we will use a framework called Langchain. Langchain is the most widely used framework to develop large language model applications. It orchestrates models, prompts, data sources, and outputs. The central idea here is a chain. A chain is an execution step in a large language model application. So it is the equivalent of a Lego block. So with Langchain, we turn building large language model applications into putting together many Lego blocks to make a castle to build an app. So go to app/app.py and follow the instruction here. There are a series of exercises from creating a model, defining a prompt, building a chain, to integrating the chain into our Chainlit application. Good luck. Welcome back. Hope you enjoyed building your own simple version of ChatGPT. So let's walk through the exercises. Here, the first exercise, we will define a model. Let's say here we'll do model equals to GPT 3.5-turbo-16K-0613. And let's set streaming equals to true, so we can see the tokens streaming back one by one. And this helps a lot with the user experience. Now, let's go down to the next exercise, a prompt template. Here is my version. We will start with a system prompt. You are Chainlit GPT, a helpful assistant. And then we will add the user prompt. It says human. And here I will define my prompt template variable as question. So whenever we substitute the model call with question variable, then it will get replaced in here. Then the next step is to set up the chain. So we will set up the chain right here. For large language model, we will use the model we have just created. And the prompt, we will use the prompt that we just created. And here we save the chain into the user session. So whenever we get on message, we will retrieve the chain from the user session. And then here is where we integrate back to Chainlit. So here we will input question equals to message.content, which means we are going to grab the message content and put that in to our question variable to substitute in the question here. And this completes the application. So now we can try to run the application using Chainlit run app/app.py-w, and this should bring up our chat application. And here is our chat application. Right now, it is using GPT 3.5 to respond. So let's say if we type in, hello world, it will say, hello, how can I assist you today? So that's it. We just built our own very simple version of ChatGPT. Feel free to play around with the application that we just built. And next, we will discuss the limitations of large language models. We have just built a simplified version of ChatGPT. Feel free to play around with the application. The technology is truly amazing. However, there are limits to what they can do. First of all, the now famous hallucination problem. Hallucination is defined as when a large language model generates a response that is not grounded in its training data or the information contained in the input prompt. The cause is that a model has no knowledge about a concept that is not part of its training data. So when asked about the latest information, ChatGPT frequently responds with, "My knowledge cutoff date is X." As an example, who is the current president of Argentina? It will say, "As my last update in September 2021, etc., etc., etc." It is common that large language models would hallucinate and generate some answers that might not be factual when asked about things it did not know. This could be a good thing for certain use cases, such as creative writing. The second type of hallucination is the misalignment between user expectations and model outputs due to simple and imprecise prompts. For example, if we ask, "What is this?" and the large language model is going to respond, but it lacks the context, so it might not understand and fulfill users' expectations. It is very important to know that our language model only predicts the next token, so the output has the highest probability to look like the right answer. The model does not understand or know what is the right answer, nor does it have a world model to reason for the right answer. To bridge this gap in models' knowledge, we could provide models information inside the prompt, so it has the required context to answer the questions. This brings us to the second limitation of large language model. All large language models have limited input context length. For example, OpenAI models has context length between 4,000 to 100,000 tokens. There has been a lot of effort to increase context length, but we have to work around with the limits. This does mean we cannot put in arbitrary amount of information into the context because there is a limit. In addition, we find that models sometimes loses focus and attention when the input context length grows too long. It's just like us humans remembering things. When there's too much things to remember, we tend to lose focus, and the model behaves similarly. So now we know large language model have some limits. We will propose a way to fix it in the next chapter so our chat with PDF application can respond to users with the right answers. We built a simplified ChatGPT application using Langchain and Chainlit. In this chapter, we will try to bring knowledge into our chat with PDF application via PDF document. We mentioned that in the previous video, a large language model tends to hallucinate, and we can fix that by putting information in the input context. But the context length is not infinite to fit all of the information out there. And the solution to this problem is to augment the large language models with relevant knowledges with regards to the question. This architecture pattern is called Retrieval Augmented Generation, or RAG. What Retrieval Augmented Generation does is that it separates our application into two portions. On one hand, we have the large language model, and on the other, we have a search engine. So on the large language model side, it is responsible for generating and reasoning the answers. On the other side, we rely on the search engine to surface the most relevant documents for us to send in to the context for the large language model. So when a user asks a question to our chat with PDF application, our application will first pass the question to the search engine. Then the search engine retrieves the most relevant documents and sends those relevant documents back to the application. Then our application includes those relevant documents inside the prompt to the large language model. Then the large language model responds to users' question with the relevant information supported by sources from our search engine. And this completes a retrieval augmented generation process. In summary, the RAG architecture uses the large language model to conduct reasoning and generation and get the factual context from the search engines. The RAG architecture is a very, very good concept, but it also has some limitations where there is no guarantee that the generated sentences will be supported by the citations, or does it guarantee all retrieved citations can be used and will be used in the generation process. In summary, we enhance the capabilities of our application by using a Retrieval Augmented Generation architecture, or RAG architecture. It first retrieves the relevant documents, provide those documents to the large language model, and when we ask the model to answer the question using the context and context only, this provides grounding to the model's answers. Now, since we brought up a search engine, we will go into a brief introduction on what is a search engine. In the last video, we discussed how we can use Retrieval Augmented Generation, or RAG, architecture to support a large language model with knowledge for it to provide answers based on sources. In this video, we will discuss the retrieval portion of the architecture. The system we use to store and retrieve information is called a search engine. A search engine is an information retrieval system designed to help us find information stored on a computer system. The most famous search engine out there is Google, which is a system that searches the whole internet. There are also domain-specific search engines that allow users to discover information, such as legal search, financial document search. And one of the latest type of search engine that we could use to retrieve information is called vector databases. And all these search engines are very similar to our physical libraries. There are primarily two processes in a search engine system: indexing and searching. Before we can search anything, we have to parse and index the information. Good parsing and indexing facilitates fast and relevant information retrieval. This is similar to librarians indexing the books to facilitate readers to find books they want to read with ease. Once the information has been indexed, then the user can start the search. Users will use the search engine to find the relevant pieces of information. Search, by definition, is incomplete and might not always return the perfect result, as our search engines might not have all of the information. There are many types of search algorithms, including keyword search, Boolean search, vector search, embedding search, and a combination of the above. So in summary, search engines have two processes. First, we have to parse and index the data into the search engine. Then, users will be able to retrieve relevant documents from the index. In the next video, we'll dive deeper into the search process. In the last video, we went through the retrieval part of the RAG architecture. We also briefly discussed indexing and searching. Now, let's dive deeper into search, specifically embedding search. Embedding search is currently the most popular way to search for an LLM application. What is embedding? Embedding is a low-dimensional representation of data. It is calculated using an encoder model where we input a chunk of text and the models output the embedding. The output is an array of floating point numbers. Embeddings contains semantic information, including its meaning and the sentence structure. And one of the key features of this is that sentences are similar, will be numerically close to each other, and this allows us to search for this where we input a chunk of text and the models output the embedding. The output is an array of floating point numbers. Embeddings contains semantic information, including its meaning and the sentence structure. And one of the key features of this is that sentences are similar, will be numerically close to each other, and this allows us to search by similarities. Then input a chunk of text, and the models output the embedding. The output is an array of floating point numbers. Embeddings contains semantic information, including its meaning and the sentence structure. And one of the key features of this is that sentences are similar, will be numerically close to each other, and this allows us to search by similarities. The way we measure how close the sentences are is by using something called cosine similarity. It is the angular distance between two embeddings. The embedding model learned to predict that similar sentences are closer to each other and different sentences are farther away. This is an extremely powerful concept. In the old days, we will need to search for exact match. As an example, when we search for the word USA or United States of America, it used to require multiple different searches because those are spelled differently. But now, with embedding search, USA, United States, and America will be all close to each other semantically, so they will show up all together. Now we capture the meanings and structures of the underlying sentences. We can then search by retrieving the top K similar documents around the questions asked, measured in cosine similarity. This algorithm is called K-nearest neighbors, or KNN. And when there is a massive amount of data, we can use a more approximate model called approximate nearest neighbor search, and this improves the latency by sacrificing a little bit of relevancy. In summary, embeddings are low-dimensional, loosey representation that enables us to retrieve relevant documents using KNN or ANN. And the way we measure similarity is cosine similarity. Again, as usual, there are certain limitations to embedding models, and we'll discuss them next. We discussed the embedding search for retrieval part of RAG architecture. In this video, we will discuss some of the limitations and the workaround we have to do to make them functional. One of the biggest limitations of embedding model is that they also have limited input. The overall input length typically ranges from 384 tokens for open source models to up to around 8,000 tokens for OpenAI models. So what do we do? One of the easiest way is just truncate the documents after they pass the input limits. This makes sense for certain applications, but for a lot of other applications, we don't want to lose information. So the common approach is then chunk the document into pieces. While we do that, we will try to keep track of the document chunks in the metadata so we know where they came from. Now here's another challenge. When we say chunk the document, how do we chunk the long documents? We can sometimes chunk documents without any overlaps, or we can chunk document by line returns, by periods, by commas, etc., etc. One common approach is to chunk document with some overlaps, so each chunk include part of the previous chunk and some part of the next chunk. This is similar to TV shows where they typically include recap of the previous episode in the beginning and the preview of the next episode towards the end. Another approach is we could create several search indices, each with different chunk size, and we can search across multiple. More importantly, when we chunk documents, we do need to budget the context length for large language models. As an example, when we retrieve top 5 relevant documents from search engine for a large language model, and the model has 16,000 maximum length, we will need to budget so that the sum of the chunk size does not go beyond 16,000 token length. And we also need to leave some room for users' question and the model's answer. So in summary, embeddings is generated by embedding models. They have limited input length, so we need to chunk the documents to work around the limitation. In addition, because large language models have limited context length as well, we need to budget our chunk sizes with that in mind. Now, armed with this information, let's continue to build our chat with PDF application. In the next session, we will add the feature of loading and processing PDF files to our application. We will add the feature of loading and processing PDF to our chat with PDF application. In this lab, we will use Langchain's PDF processing connectors to load PDF. And we will chunk it using Langchain's document transformers. And finally, we will use Chainlit's ask file message to ask the user to input their own PDF documents. Please go through the exercises here in app.py. Feel free to use Google search or visit Langchain's and Chainlit's documentation. Good luck. So let's go to app/app.py. Let's first load the PDF file. We will use PDF Plumber loader to load the temporary file that user have uploaded, and then we can use loader.load. There are a wide variety of PDF loaders in the Langchain library, and I am picking PDF Plumber only because I am familiar with it. You are free to use other PDF loader as well. After we load the PDF file, the file is long, so we will have to chunk them into smaller documents, as we mentioned previously. So we will use one of Langchain's document transformer called Recursive Character Text Splitter to split our document into pieces. As we mentioned in the previous videos, we do have to budget and keep in mind about large language models' context length. Since we're using GPT-3.5 16K, it has 16K context length. So if we set chunk size to 3,000 and we are retrieving 5 tokens per chunk, and if we retrieve the top 5 documents, this means at most we will have 15,000 tokens in the context, and this leaves around 1,000 tokens for our input questions and output answers. And just to retain better context, let's add a chunk overlap to, let's say, 100. Which means every single chunk is going to include 100 tokens from the previous and the next chunk. Now we build our text splitter, then let's use the text splitter to split documents that we have loaded previously using our PDF loader. So this concludes the document loading and document chunking process of our chat with PDF application. Since our chat with PDF application allows user to chat with PDF, in order to do so, we have to ask the user to upload a PDF before the chat session starts. So at chat start, we will send user a message, ask file message to ask user for file, and then we will say, please upload the content. We will accept PDF documents only, so application PDF, and then we will set the max file size to 10 megabytes just for safety and security. And once we create the ask file message, we will send to the terminal so the user can see our message. With this, we build in the capability to ask user to upload a file, and then we load the PDF document and we chunk the document. Now let's give the application a spin. We can do so by chainlit run app/app.py -w. And now you can see our prompt. Please upload the PDF file you want to ask questions against. We have provided a sample PDF here, so please download it to your local directory. And what we will do here in our chat application is we will browse the files, we will upload the sample document that we provided, and see that it says processed and it's loading, which means it's done at this point. So now we have uploaded and processed the document. In the next exercise, we will try to ingest this into our search engine so we can search against the document. We enabled document loading and developed a chunking strategy to chunk them into smaller subdocuments. Now we will need to index them into our search engine in order for us to utilize the processed document in our chat with PDF application. This is the retrieval portion of the RAG architecture. In this lab, we will implement the embedding model and index the documents we processed previously into databases using Langchain. For our search engine of choice, we will be using ChromaDB. Chroma is a lightweight vector database that can live in memory, similar to SQLite. Let's go to app/app.py. We have prepared some exercises for you to walk through. Now we are building another function called create search engine. This function takes in a list of documents and an embedding model, and it will return a vector database with documents and embeddings indexed. We will also initialize an OpenAI embeddings model as the encoder. The standard one to use is text embedding -ada-002. Please initialize it using Langchain. We can then pass in the model and the list of processed documents into our create search engine function and get a vector database with all the data we have inside. Let's go to work. In this video, we will go through the solution. In our create search engine function, we will be using Chroma as the search engine. We will utilize Langchain's Chroma from documents as we pass in a list of documents to be ingested to our search engine. So we will do Chroma.from documents. We'll pass in the client that was already initialized in the code above. Client equals to client. Documents equal to docs. We'll use the embedding model passed in to embed the documents, and we will use the exact same client settings as we created above. Then we will define our embedding model here using OpenAI embeddings. We will use model equals to text embedding ada-002. That's it. Now our function to ingest document into our search engine is done. We have both the document processing pipeline and the search engine indexing pipeline ready. Next step, we will tie everything together and integrate everything into our Chainlit application so users can finally ask questions, PDF document upload and processing, and we build a search engine to ingest the documents. In this lab, we are going to put everything together and create a full chat with PDF application using Langchain. So let's first navigate to app.py. On chat start, we first ask the users to upload a PDF file. Then we load and chunk the PDF file and ingest them into our Chroma search engine. Now we will have to create our chain to retrieve with QA. So this is the retrieval augmented generation portion. When we retrieve, usually we would like to retrieve sources as well to provide to the users so they have grounding and trust to the documents and the answers that we provided. This is super exciting. Let's get to work. The solution portion of our lab, let's navigate to app/app.py where we need to implement our chain. Because we want to retrieve with sources, so we will use the retrieval QA with sources chain. We will initialize it from chain type, and we will pass in a large language model. And the large language model is the model we define here. We will want to set the temperature to 0, specifically because temperature ranges between 0 to 2, where 0 means the model is not going to be very imaginative, and when temperature is 2, it means model can produce more creative answers. Since we are talking to a PDF, we do not need the model to be too creative. Then we will set the chain type to stuff. This is the default type for chain, and stuff means we will send all of the retrieved documents into the context. And for retriever, we will set it to the search engine we have built previously, and we use it as retriever, and we will set the max token limit to 4097. And the only reason we set it to 4097 is because it is an artifact of our previous code. So now we have our whole application. We can now run it by chainlit run app/app.py-w, and it's going to bring up the full chat with PDF application. Now we can feel free to play around with it. So we can go to browse our files, upload the sample document, and it's going to take a little bit to process and load. And once it's loaded, it says, loaded, you can now ask questions. So let's give it a few questions to try. What is this document? It's going to use our retrieval document chain, and it return the answer. This document is a financial report from NVIDIA Corporation. Voila. So this is our chat with PDF application. So in the next session, we will spend a little bit of time playing around with the application and find if the application is making any errors to ensure there is certain quality control. Congratulations. Now we build our own chat with PDF application. But we're not done yet, because as best practice, we always want to do some quality control and make sure the application is functional as intended. So let's spend some time play around with it. So let's upload the document again. It's going to take a little bit of time to process, and it's now loaded, and we can ask questions. So let's give it a spin. What is this document? And it uses a chain. It says financial report or statement from NVIDIA Corporation. What happened in the quarter? And it's processing, and it says in the second quarter, NVIDIA announced blah, 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 blah. And one of the important questions a financial analyst or an accountant, the operating margin of the quarter. And it says the operating margin is not provided in the given information. And this is perplexing. So let's click on the sources, and we can see this is some parsed financial statements. And here we do see that there is gross margin, gross profit, and there is also operating expenses and operating income. So with operating income, the model should be able to know the operating margin, but it says the operating margin is not provided. So this is a bug, because we as a user would expect the model to know this from the provided information. So in the next chapter, we will go through prompt engineering, and we'll utilize a technique called prompt engineering to fix this problem. We have identified a deficiency in our chat with PDF application. It said that the PDF file does not contain enough information for one of the key questions we want to ask, despite there is enough evidence in the documents to answer. To address this issue, we can solve this by prompt engineering. We define prompt engineering as an engineered approach to communicate with LLMs to steer its behavior for the desired outcomes without updating model weights. It is a highly empirical method. First and foremost, we have to be very specific and explicit, leaving very little room for the model to misinterpret. This is similar to providing instructions to children. So, to make our discussion more structured, we are introducing a prompt engineering framework called RACEF. It's RASCEF. It stands for roles, actions, steps, context, examples, and format. R stands for role-playing. We can instruct the large language model to assume a role, so it will try to behave like one. As prompt engineers, we have the liberty to expand and define what the role does, and even the potential character to undertake if necessary. An example would be, please act as an expert product manager like Steve Jobs when you respond to user requests. This is effective for common job titles and roles, but less effective for the less common roles. Next, the A stands for action. It's the action that we want the large language model to take. For example, summarize, answer, extract, copyright, revise, etc. Again, we have to be very specific with the action required for the intended results. Next, S in the RACEF framework stands for steps. This is where we instruct the model to either explicitly follow certain steps or for the model to think step by step before it acts. The C in the framework stands for context. Sometimes the model might not have the right context or knowledge to answer our questions. As we have done in the previous lab, we use the Retrieval Augmented Generation architecture to provide relevant context for the model to respond to our request. The E in the RACEF framework stands for examples. For school or homework problems, it is very common for the teacher to provide a few examples and answers to the students so the students can mimic and learn from those examples. Language model behaves very similarly. We provide it with examples on how to answer questions to allow it to better answer to our request. Finally, the F in RACEF stands for format. In our previous lab, you see that we put the format in a stream pass-through. This way, we can betterize the model output for downstream applications. Sometimes we want the model to output a structured JSON format to better connect with the next step, and sometimes we just want the model to output a string to tell a story. So as an example, on the left here, we let the model output a unstructured free-form generation. And on the right, we ask the model to provide the answer in a JSON schema format so it produces a JSON output. And this JSON output can be later parsed for downstream usage. In summary, prompt engineering is an engineered approach to guide the model to generate the desired output. We can utilize the RACEF framework to instruct the model. Before we can engineer the prompt for our application, we have to try to first extract the prompt template used in our Chat with PDF application and put them in an easily editable location. So next, we will go through a lab to extract the prompt template to enable prompt engineering in our application. We will set up prompting for our Chat with PDF application. This will enable us to apply prompt engineering methods to fix the deficiencies of our Chat with PDF application to produce the desired outcomes. In order to do that, we need to first extract the prompt template for our codebase. We will then put them into the prompt.py file in the app folder. Then we will go to apps and import the prompts from our prompt.py file. And finally, we will add the prompts as part of our keyword arguments when we initialize our retrieval chain. One important trick, we can jump into the source of a piece of code by control-click or command-click on the functions or import statements. This will help you navigate the codebase very quickly. As a demo, let's find our retrieval QA with sources chain, click on it, and it will jump to where this is defined. This exercise is to navigate and read the source code to figure out where and what are the prompts. Then we can extract and copy them into prompts.py. This is going to be a fun one and very different from writing code. Good luck. Now let's go through how to navigate the application to find and extract the exact prompt. First, we go to app.py and find retrieval QA with sources chain, and we command or control click on it to navigate to retrieval QA with chain, the source code. We scroll around and we don't see anything that's interesting here about prompt templates. So let's navigate to its base class, which is base QA with sources chain. Since we initialize the chain from chain type, we can see here there's a chain type key args. This means this is the keyword argument for the chain type that we input. And in this function, we see a load QA with sources chain. So let's click on here and jump to the load QA with sources chain function. We navigate down here and we see that it uses the load stuff chain function here. So let's click on the load stuff chain function, and voila, this is the prompt. So we do see the prompt is base prompt template, and then there's a document prompt. It's base prompt template, stuff prompt, example prompt. So if we navigate by clicking on the stuff prompt, we can see the full prompt template that is used in our current Chat with PDF application. So let's go ahead and copy paste the whole thing into our prompts.py. And here we're done. Let's do a little bit of cleanup here, just so it's clean. Save this, and then we go to app.py and import the prompt template into our application. So it was prompt and example prompt that we need to import. And then when we initialize our chain here, we can then input, just as a reminder, let's go back to base QA with sources chain. We see that it uses chain type key args. So let's use this parameter and then set it to prompt equals to prompt document prompt as example prompt. And here we are done enabling our application to have its own prompt template. Then we will give it a spin just to make sure that everything runs. So we will do chainlit run app/app.py-w, and hopefully everything loads. And once the application is loaded, we know that it is working. So let's open in the browser. Boom, boom, boom. Browse files, downloads, NVIDIA, and it is now running. So next, we will dive into the toolings to help our prompt engineering efforts. In this video, we will go through how to operate a prompt playground that's built in Chainlit. The prompt playground will greatly accelerate the prompt iteration process and allow us to see the results in real time. Now let's start the application and upload a simple PDF file. And then let's start asking questions. The question we had the problem with is, what is the operating margin? So that's going to ask this question. And it says the operating margin is not provided in the given information. From here, we can see that it took one step. So let's click on the downward pointing arrow to expand this. And it says took 2 steps. Let's expand that again. And here is the retriever doing its work, retrieving the documents. And then it goes to stuff documents chain, and it took 1 step. And it calls the end chain, it took 1 step. And the result is the operating margin is not provided. So now here is a little bug icon. So if we click on this, we can inspect everything in the prompt playground. So click on this and it will navigate to Chainlit's prompt playground. Here we can see the exact prompt that is sent to the OpenAI API. And if we scroll all the way back down, it's a long one, but if we scroll all the way back down, we can see the assistant replying with the message. And this is the exact responses that we get. On the right-hand side, we can choose to use different LLM providers. So let's stick with Chat OpenAI, and we can choose different models to use. Right here, we have GPT-3.5 Turbo, Turbo 16K, GPT-4, and different temperature and different max token sessions, and a whole bunch of knobs that we can use to tune. As a reminder, temperature, the higher value will make the output more random, and the lower value will make it more focused. And if we click on submit, it is going to run the whole chain again. So this is the prompt playground, and we can use this to accelerate our prompt engineering efforts and attempts. And just a reminder, sometimes some of the models might not be available to you depending on your OpenAI subscription. So with this, in the next lab, we will use the prompt playground extensively to fix the deficiencies in our Chat with PDF application. we will put our new tool to work. We will utilize Chainlit's prompt playground to diagnose and fix the prompt to correct the deficiencies that we observed. So let's review how to get to prompt playground. We will browse the file, upload our simple PDF document. It's going to take a bit to load. And now we will ask the question that it wasn't able to answer. What is the operating margin? And we will expand with all the steps, goes to the bottom of the chain, and then click on the bug icon, and this brings us to the prompt playground. As a reminder, please feel free to review our prompt engineering lesson and the Retrieval framework. Now, let's work to make our chat with PDF application to produce the right answers. Have fun iterating on the prompts with all the possibilities and all the knobs that we can tune. There are many ways to resolve this problem, and here I will demonstrate my solution. Your solution might be different, but as long as it produces the intended results, it's awesome. So let's start by uploading the document again and ask the question we want to fix. Is the operating margin? And let's navigate down to the prompt playground. Click on this little bug icon, and we are in the prompt playground. So the first thing we will do is we will investigate what is the current prompt. So the current prompt provides the actions that it wants to do first by saying, given the extracted part of a long document and a question, create a final question with references. If you don't know the answer, just say that you don't know. Don't try to make up the answer. So this is the action in the Retrieval framework. And it says, always return a sources part in your answer. So this is the format, the F of Retrieval. Then it goes on to ask a question with some context. The first question is, which state country law governs the interpretation of the contract? And it goes on providing the right information. And then the second question is, what did the president say about Michael Jackson? And it uses certain script from somewhere else. And then it provides an example answer. This, because it provided two examples on how to answer questions. This is called two-shot or few-shot learning. And then we can see our actual question. What is the operating margin? And then the extracted or relevant document that we provided to the prompt. So now with that, we can start by editing or by prompt engineering. First, for me, I feel that these two examples are not too relevant to the financial documents that we are looking at. Specifically, they are closer to a prose instead of some semi-structured financial documents. So let's remove these two examples. So let's go back here, select, remove the examples. Then, since we are providing a source field, let's just make it even more explicit. So always return a sources part in your answer with the format sources, source 1, source 2, etc. And since while we are at it, let's make sure and provide it a role to play. And the role we want to assign it is a financial analyst, since we're dealing with a financial document or financial press release. So let's do this. Please act as an expert financial analyst when you answer the questions. And because we are dealing with some sort of financial document, so that's and pay attention to the financial statements. And one of the reasons that the model could not get what an operating margin is might be that it doesn't know what the definition of operating margin is. So that's spell out the steps it needs to take to calculate the operating margin. So operating margin is also known as op margin and is calculated by dividing operating income by revenue. So now we change the prompt by assigning the model a role, provide the steps it needs to calculate the operating margin, remove irrelevant examples, and provide more explicit sources using our Retrieval framework. So let's give this a spin and see how the model behaves now. So now the answer is clear. The operating margin is a measure of company's profitability, etc., and it goes on, get the operating income, and then get the revenue, and calculates the operating margin to be 50.3%. So this is a success. Now, let's take our newly formatted prompt, right-click, copy, and put it in our prompt template. So we will put in the template here, and then we also remove the examples. So let's remove the examples. And then we can save the prompt, and the application is going to hot reload. And we can go back to our chatbot, browse the file, upload the same file again. It's going to take a while to load, and ask the question that we had problem before. What is the operating margin? And fingers crossed, 50.3%. So with this, we just used prompt engineering, apply our Retrieval framework, and fix a problem the model couldn't solve earlier. In the future, we might run into more problems, so we'll repeat the same process and collect a set of questions and expected outputs for our testing dataset. So now, our chat with PDF is now robust enough to answer our questions. We have reached the end of our journey together. First off, a huge thank you for joining me in this course. It has been an incredible experience sharing my knowledge and passion for large language models with you. You have taken the first big step towards mastering a technology that is shaping our world. The world of large language models is ever evolving, so I encourage you to keep exploring. Start by applying what you have learned. Maybe refine your chat with PDF application and apply the RAG pattern to other data sources. There are plenty of resources out there to help you along the way. Websites like GitHub, Stack Overflow, and AI-focused Reddit are great places to start. And don't forget books and other LinkedIn learning courses. They are invaluable to deepening your understanding. Want to continue this learning journey with me and the others? Dive into the Q&A feature of this course to ask questions and share your experiences. I am looking forward to seeing you using your skills to solve real problems. So go out there, experiment, create, and don't be afraid to push the boundaries of what is possible. Good luck.